Hello everyone, welcome back to MP Coding's Linux device driver development with Raspberry Pi tutorial series. In the last video, we covered the Linux device model. We registered a custom bus, a device, and a driver. The kernel bound them together and probe fired automatically. But at that point, user space had no real way to interact with the driver, beyond just knowing it existed somewhere in Sysfs. This video changes that. Sysfs attributes are how a driver exposes its internal state to user space, as simple files /sys. Reading a file calls the show function. Writing a file calls the store function. No I/O control, no custom character device protocol, no complex API, just plain files. And this is one of the things that makes Linux driver development elegant. We expose our driver's data through the file system. User space reads and writes it like any other file. If you have been following the series, we have actually used this concept several times in this tutorial series, but today we will discuss it in detail. In this video, we're going to cover three things. First, device attributes, what they are, and how the device ATTR macro works under the hood. Second, creating and removing Sysfs files, the full lifecycle of an attribute file, from probe all the way through to remove. And third, the class interface, how to expose attributes under /sys/class/mydriver, and how that automatically triggers Udev to create a /dev node. Okay, let's start with device attributes. A device attribute is simply a file in Sysfs that represents one property of a device. The kernel gives us the device_attr macro to define them cleanly without writing a lot of boilerplate code. So let's look at how this macro works. Device_attr takes 4 arguments. The first one is the name. This is the file name that will appear in Sysfs. So if we pass value, we get a file called value under our device's Sysfs directory. The second is the mode, the file permissions. 0444 means read-only, so user space can only read it. 0644 means read and write, so user space can both read and write. And 0200 means write-only. The third is show. This is the function the kernel calls when user space reads the file. Think of it as the cat handler. And the fourth is store. This is the function called when user space writes to the file. Think of it as the echo handler. If you don't need write support, just pass null here, and the file becomes read-only regardless of the permissions. Now there's one important thing the macro does behind the scenes. It doesn't just wire up the callbacks. It also defines a variable with the prefix dev_attr_ followed by the name. So if the attribute is called value, the macro creates a variable called dev_attr_ value. We'll use that variable later when creating and removing the file, so keep that naming in mind. Let me show you 2 simple examples, a read-only name attribute and a read-write value attribute. But before we look at the macro, let me show you what's actually happening underneath it. Because device_attr is not doing anything magical, it's just filling in a struct device_attribute for you. So for the name attribute, what the macro actually creates is a device_attribute struct called dev_attr_name, with the attribute name set to name, the mode set to 0444 for read-only, and the show pointer set to the name_show function. That's it. That's all it does. And we can write it out manually if we want, or we can just use device_attr and let the macro do the same thing in one line. The result is identical. Same idea for the value attribute. The struct is called dev_attr_ value. Mode is 0644 for read and write, and this time we wire up both show and store. Again, we can write the struct like this, or use the macro. Same result. Now let's look at the 2 callback functions, show and store. First, the show callback. Show is called when user space reads the attribute file. So whenever someone runs cat on it, it receives 3 things, a pointer to the device, a pointer to the attribute, and a page-sized buffer to write the output into. Inside the function, the first thing we do is call container_of to get back to our own my_device struct from the generic struct device pointer the kernel hands us. We've seen this pattern before in the LDM example. Same concept, just applied here inside a Sysfs callback. Then we write the value into the buffer using snprintf and return. 3 things to keep in mind here. First, always end your output string with a new line character. Tools like cat expect it, and without it your output will run straight into the shell prompt on the same line. Second, return the number of bytes written. snprintf already returns that for you, so just return what it gives you. And container_of is not the only way to get your private data. If you stored your device as a pointer inside a structure field rather than embedding it, you would use dev_get_drv data instead. Either way, the goal is the same. Get back to your own data from the generic device pointer the kernel passes in. Now the store callback. Store is called when user space writes to the attribute file. So whenever someone runs echo on it, it receives the device pointer, the attribute, the input buffer, and the byte count. Same container_of pattern to get our struct back. Then we parse the input using kString_to_integer method to update our value, and then return the count value. There are 3 important rules for store. First, always use string to integer, string to unsigned long, or string to boolean to parse user input. Never use scanf directly on data coming from user space. The string to family handles white space, new lines, and invalid inputs safely. Second, always return count on success, not 0. This is a very common mistake. If you return 0, the kernel thinks nothing was written and will keep calling store in a loop. And third, validate the input before you apply it to your hardware state. If the value is out of range, return a negative error number and reject it. Never blindly apply whatever the user wrote. Now let's look at how to actually create and remove Sysfs files. And this is an important point. Defining the attribute with device_attr does not create the file. The macro just prepares the attribute struct. We still have to explicitly create and remove the file ourselves around the device's lifetime. Creating the file is done with device_create_file. And the rule here is simple. The device must already exist in Sysfs before we can add files to it. So we call device_create_file after device_register. Or in our platform driver case, inside probe function. We pass it the device pointer and a reference to our attribute variable, the dev_attr_name, that device_attr created. If it fails, we can log the error and return the error code. After this call succeeds, the file exists under device's Sysfs directory and is immediately readable from user space. Removing the file is done with device_remove_file. And here the rule is the opposite. We must remove the attribute file before we unregister the device. If we unregister the device first and then try to remove its attribute files, the kernel will throw a warning about dangling Sysfs entries because the device directory is already gone. So in remove, device_move_file goes first. Then device_unregister follows after. The rule to remember is straightforward. Create after register, remove before unregister. Always reverse order on cleanup. This pattern comes up over and over in kernel driver writing, not just for Sysfs files, but for everything. Resources, IRQs, memory. Whatever create last, destroy it first. Now what if we have more than one attribute? The straightforward approach is to call device_create_file for each one separately. But here's the important thing. If any of those calls fail, we have to undo the ones that already succeeded before returning the error. This is the same error path pattern we talked about in the LDM example. So in probe, we create name attribute first. If that fails, we return immediately, nothing to clean up yet. Then we create value. If that one fails, we have to remove name first before returning the error. Otherwise, name is left as a dangling file with nothing behind it. In remove function, we go in reverse order, value first, then name. Always reverse of how you created them. Now, Doing this manually for every attribute is fine when you have 2 or 3. But once you start adding more, it gets tedious and error-prone. That's where sysfs_create_group comes in. Instead of calling device_create_file for each attribute individually, put all the attributes into an array, wrap that in an attribute_group struct, and then create them all in a single call. Notice the array ends with a null sentinel. The kernel uses that to know where the list ends. Same pattern as of _device_id match tables from the SPI and I2C examples. Then in probe, one call to sysfs_create_group creates all the files at once. And in remove, one call to sysfs_remove_group removes all of them. If any file fails to create during the group call, the kernel handles the partial and cleanup automatically, which is the other big advantage over doing it manually. Notice we pass Kobject directly here. We're working on the Kobject level here, which connects back to what we learned about Kobjects being the foundation of the device model. Now let's talk about the class interface. /sys/class. Device attributes /sys/devices are useful for device-specific data, but for a cleaner user-facing interface, and for automatic /dev node creation, we use the class interface instead. A class groups devices by function. The class interface exposes a directory under /sys/class/mydriver that user space and Udev can reliably find, regardless of which bus the device is on. Now, registering and unregistering a class is something we already covered in detail in the character device driver development tutorial. So I'm not going to go through all of that again here. If you missed that video, go back and watch it. But in today's example, I'll use the class interface to demonstrate everything we're talking about, so you'll see it working in practice. The flow is straightforward. First, we create the class. Then, inside probe, we create a device under that class. After that, the sysfs tree looks like this. Under /sys/class/mydriver/mydev0, we get a dev file containing the major and minor number. That's what Udev reads to call mknode and create the /dev/mydev0 node automatically. We get a uevent file, and any attributes we add with device_create_file appear right there alongside them, under /sys/class/mydriver/mydev0, not under /sys/devices. This is the path that user space tools typically look at, which is why the class interface is the preferred way to expose driver data. Let me also show you the full flow from module_init all the way through to module_exit, so you can see how everything fits together. Module_init creates the class first, registers the bus, then registers the driver. The driver registration triggers match, which fires probe. Inside probe, device_create creates the class device, which sends a uevent and Udev creates /dev/mydev0 automatically. Then device_create_file adds the attribute files under the class device. And on the way out, module_exit, we go in strict reverse order. Attribute files removed first, then the class device destroyed, then the char device region released, then the driver unregistered, then the bus unregistered, and finally the class destroyed last. Now let's quickly cover the advanced topics before we jump into the example. Let's look at the binary attributes. Standard device_attr attributes are text-based. Everything goes through strings. Binary attributes skip that and let you read and write raw binary data directly. This is useful for things like firmware blobs or calibration data where strings don't make sense. We can define binary attribute using bin_attr, similar to device_attr, but for raw data. The read and write callbacks work just like file_operations read and write, receiving a raw buffer and an offset. You create and remove them with device_create_bin_file and device_remove_bin_file. The same lifecycle rules apply. Now let's understand Sysfs notify system, alerting user space without polling. Normally, If user space wants to detect a change in a sysfs value, it has to keep reading the file in a loop, busy polling. Sysfs_notify solves that problem cleanly. When something changes inside our driver, like from an IRQ handler or a work queue, we can call sysfs_notify on that attribute. Any user space process that called poll or select on that sysfs file gets woken up immediately. No busy loop, no wasted CPU cycles. The driver notifies, user space reacts. This is the right pattern for things like sensor readings that update from hardware interrupts. Rather than making user space poll every 100 milliseconds, you just notify when something actually changes. I've linked the references I used to put this material together in the description. Definitely take a look at those, especially Linux device drivers, 3rd edition. It's one of the best resources for understanding this stuff deeply, and it's worth reading even if you just go through the relevant chapters. All right, enough theory. Let's go to the example. Now let's go through the example code. I've wrapped everything we discussed, standard attributes, attribute groups, binary attributes, and sysfs_notify, all into one single driver. Let's start from module_init. Here I've simply registered the platform device first, with this driver_name, which is simply the sysfs_ex, and then registered the platform driver. That's it, clean and simple. And notice something important. I have not created the character device or the class here in module_init. In the earlier explanation, I showed it being done in module_init, and that's one valid way to do it. But in this example, I'm showing you how real drivers typically do it. Everything happens inside probe. The kernel calls probe when the device and driver are matched, and that's where you bring the hardware to life. In module exit, we just reverse init. Unregister the platform driver first, then unregister the platform device. Now let's look at what sensor_driver is. It's a platform_driver struct. Its probe function is sensor_probe. Its remove function is sensor_remove. And its name matches the platform device name, driver_name. That name match is what causes the platform bus to bind them together and call probe. Now let's go into sensor_probe. The first thing you'll notice is struct sensor_dev. This is our private driver data structure. It holds everything belonging to this driver in one place. Inside it, we have a namechar array to store the sensor name string, and value as a simple integer, our simulated sensor reading. Then blob, a byte array to hold fake calibration data for the binary attribute demo. Then the important character device fields, dev_nr to store the device number, and c_dev for the cdev struct. We covered these in the character device driver tutorial. The difference here is that instead of putting these in global scope, they're inside the private data struct, which is the proper way to do it in a real driver. Then pointers for the class object, the class device, and the platform device. A delayed_work struct for the work queue, and a mutex for protecting shared data. Back in probe, let's walk through it step by step. First, we allocate the private data using dem_kz alloc, device managed, so it's freed automatically when the device is removed. Then we store the platform device pointer. Then call platform_set_darv data to attach our private data to the device. And then initialize the mutex. Then we set up the simulated hardware state. Copy mysensor0 into the name field. Set value to 0. And fill the blob with 0xAB hex value as fake calibration data. Next, alloc_shrdev_region allocates the character device number. Then we initialize the cdev with an empty file_operation struct, just a placeholder for this example. And call cdev_add to register it with the kernel. Then class_create creates the class. This gives us /sys/class/mysensor. And device_create creates the device under that class, giving us /sys/class/mysensor /mysensor0 and triggering Udev to create /dev/mysensor0 automatically. Everything up to this point follows the same pattern we covered in the character device driver tutorial. Now comes the Sysfs attribute registration, and this is the new part. First, device_create_file for dev_ATR_name. This device attribute name variable was created for us by device_ATTR_RO. The RO suffix means read-only, and it's just a shorter version of the full device_ATTR macro. If you hover over it in your editor, you'll see it just defines the device_attribute struct for us. Same thing we discussed earlier. Then device_create_file for dev_ATTR_value. Same idea, but device_ATTR_RW. This time because we need both read and write. Next, the attribute group. Let me show you what config_group is. It's an attribute_group struct with .name set to config. That name is what creates the config subdirectory under mysensor0. Inside it, config_attrs is the attribute array. It holds mode and threshold, both with show and store callbacks. And notice the last element of the array is set to null. That's mandatory. That's how the kernel knows where the array ends. Back in probe, we call Sysfs_create_group to create the whole group at once. Notice the first argument. It's Kobject. The function works at the Kobject level, so we need to pass the Kobject from our class device. Then the binary attribute. We call device_create_bin_file and pass the bin_attr_calibration. Let me show you what that is. It's defined with bin_attr, similar to device_attr, but for raw binary data. It has a name, a mode of 0644 for the read and write callback functions, and the blob size, which we've set to 16 bytes. I'll walk through what these callbacks do in a moment. Now, if any of those creation calls fail, we jump into the error path. And as always, we undo in strict reverse order. Group, then value, then name, then destroy the device, then destroy the class, then unregister the char device region. Make sure you always follow this order. If everything succeeds, the last thing we do in probe is schedule the delayed work. init_delayed_work sets it up, and schedule_delayed_work fires it after 5 seconds. I'll explain what sensor_work_fn does in a minute. Now let's look at sensor_remove. The very first thing we do is cancel delayed work sync. This is critical. It stops the work queue and waits for any currently running work to finish before continuing. You must do this before removing any Sysfs entries. If the work queue fires a sysfs_notify after the Sysfs files are already gone, you'll get a kernel crash. Then everything else is removed in reverse order. Binary attribute, group, value attribute, name attribute, device destroyed, class destroyed, and finally the char device region unregistered. Now let's look at the attribute callback functions. Name_show function. Simple. It calls dev_get_drv data to get our private sensor_dev struct back from the device pointer. Then copies the name string into the user buffer. Value_show function. First get the private data. Then takes the mutex. Reads the current value. Releases the mutex. And writes it into the buffer as a string. Remember, standard Sysfs attributes are always strings, even for integers. Value_store function gets the private data back as before. Uses kstr to int to convert the user space string into an integer. Takes the mutex. Updates the value. Releases the mutex. And then, this is the key part, calls sysfs_notify. That one call wakes up any user space process that was blocking on poll or select waiting for this file to change. Mode_show, just a dummy callback. It always returns auto. Mode_store, also a dummy. It just prints whatever string the user wrote into the kernel log. Threshold, same idea, dummy attribute. Threshold_show always returns 100. Threshold_store parses the input as an integer and logs it. Now the binary attribute callbacks. Calib_read uses kobj_to_dev to get the device from the Kobject. Then dev_get_drv data to get our private struct. It checks the offset. If we're already past the end of the blob, return 0 to signal end of data. Otherwise, clamp the count to what's available from that offset, copy from the blob into the buffer, and return the byte count. Calib_write, same offset and clamping logic, but in reverse. If offset is past the end, return no space error code. Otherwise, copy from the user buffer into the blob at the given offset and log how many bytes were written. The offset handling is important. Binary attribute reads and writes can happen in chunks, just like regular file I/O. You always have to respect the offset and never assume you're getting all the data in one call. Finally, let's look at sensor_work_fn, the delayed work callback. It uses container_of to get back to our sensor_dev struct from the embedded dwork field. This is how we can use container_of to get back to our private data field. Then it takes the mutex, increments the value to simulate a hardware sensor tick, and releases the mutex. It logs the new value. Then calls sysfs_notify on the value attribute, waking up any user space waiting on poll. And finally, it reschedules itself to fire again after another 5 seconds. So the work queue keeps running in the background, ticking every 5 seconds, updating the value, and notifying user space each time. That's the complete sysfs_notify pattern in action. All right, let's test the example. I've added detailed comments in the README file explaining each part of the code. Make sure to check that out. First, let's build it. Type make and hit enter. Wait for it to finish. I have opened the d-message log in other terminal. Okay, now let's load it. Check the kernel log. You can see probe called and module loaded printed. The platform bus matched our device and driver, and probe ran automatically. Now let's verify the sysfs tree. Navigate to /sys/class/ and you'll find the mysensor class directory we created. Our character device. And if you look inside mysensor 0, you can see all the attributes we registered: calibration, config, name, and value. Now go into config/, and there you'll find mode and threshold. That's the attribute group working exactly as we set it up, 2 attributes registered together under their own subdirectory. Let's start reading and writing. First, let's read the name attribute. It returns mysensor 0, exactly what we said in probe when we copied the name into the private data struct. The name_show callback just returns that string to user space. Now let's read the value. You can see it returns 21. That's the current value at the time we read it. You can confirm that from the kernel log. You'll see the sensor tick messages with the matching value. Now let's write a new value 12 from user space. Look at the kernel log. You can see the value was updated to 12 and sysfs_notify was sent. Let's quickly check the group attributes too: read and write of mode and threshold. Everything is working as expected. Now let's check the binary attribute. This one requires root access, so first switch to superuser. Now let's do a hex dump of the calibration blob. This reads back all 16 bytes. And you can see 0xab repeated across the entire blob, exactly what we said in probe with memset. That raw binary data is being read directly through Sysfs, no string conversion involved. Now let's write new calibration data, just the first 4 bytes. This pipes 4 raw bytes directly into the calibration file. The calib_write callback receives them with an offset of 0 and copies them into the blob. Now let's verify. And there it is. The first 4 bytes are updated, and the remaining 12 bytes are still from the original memset. The offset handling in calib_write made sure only the bytes we wrote were touched, and the rest stayed intact. And one more thing worth pointing out. If you check the /dev directory, you'll find mysensor0 there too. We never called mknode manually. We never wrote a Udev rule. The /dev node was created automatically. I have explained how this works in the character device tutorial. If you don't understand this, please watch that video. Now let me show you how Sysfs_notify actually works from the user space side. I've written a simple Python script to demonstrate this. Let me walk through what it does. First, let's run it. You can see it prints the initial value and then just waits. Now watch. Every 5 seconds when the work queue fires in the driver, Sysfs notify is called, and the script wakes up immediately and prints the new value with the timestamp. So in the code, it opens the value attribute file and does an initial read to show the current value. Then it registers the file with poll. Then it enters a loop and calls poll.poll with a 10-second timeout. It just sits there waiting. When the kernel driver calls Sysfs_notify on the value attribute, this poll call wakes up, reads the new value, prints it with a timestamp, and goes back to waiting. So in the code, it opens the value attribute file and does an initial read to show the current value. Then it registers the file with poll. Then it enters a loop and calls poll.poll with a 10-second timeout. It just sits there waiting. When the kernel driver calls Sysfs_notify on the value attribute, this poll call wakes up, reads the new value, prints it with a timestamp, and goes back to waiting. And that's it for today's video. We covered device attributes, Sysfs file lifecycle, attribute groups, binary attributes, the class interface, and Sysfs_notify, all tied together in one working example. If you want to go deeper on any of these topics, check the README files. I've added detailed comments and explanations in there for everything we covered today. And all the source code is in the GitHub repo. Link is in the description. In the next video, we're going to look at debugfs, a kernel file system specifically designed for driver debugging. It's a really useful tool, and we'll see how it compares to Sysfs for exposing driver internals. So stay tuned for that. If you found this video helpful, give it a like and subscribe to my channel so you don't miss the next one. See you in the next video.